A very good morning to all of you. Today we are going to discuss about the third type of static wire compensator. The third type of SVC, that is right here. Third type of SVC we are going to discuss. Thyristor switched capacitor. Thyristor switched capacitor dash thyristor controlled reactor. Thyristor controlled reactor, that is TSC dash TCR static wire compensator, SVC. We have earlier discussed about two other types of static wire compensators. One was mechanically switched capacitor thyristor controlled reactor, that is MSC TCR type SVC. In previous lecture we discussed the second type of SVC, which was fixed capacitor thyristor controlled reactor, that is FCTCR type SVC. And today I am going to discuss about the third and the most important type of static wire compensator, that is thyristor switched capacitor thyristor controlled reactor SVC, or TSC TCR SVC. Okay, so the two main important components are thyristor switched capacitor TSC, which is used for generation of leading wires or reactive power, and the other component is TCR thyristor controlled reactor, which is responsible for generating the lagging wires or consuming the reactive power, absorbing the reactive power. TSC generates the reactive power and TCR absorbs the reactive power. And TSC and TCR, they work in combination with each other, in coordination with each other, and hence result in a shunt compensation. Right, the schematic diagram is like this. We have a high voltage SVC bus, HV SVC bus, and then we have a step down transformer, which is also called coupling transformer. This is our coupling transformer. Coupling transformer. It steps down the voltage from high voltage level to some medium voltage level, and it creates medium voltage bus, MV SVC bus, that is medium voltage SVC bus. And then to this medium voltage SVC bus we connect TSC branch, we connect segmented TCR also. So the connections are like this. So first of all, we connect the thyristor switched capacitors. So for example, this is capacitor C1 and this is TSC S1. The total applied voltage across TSC branch is V. This is the total applied voltage, RMS value of voltage. And then we may have a number of TSC branches in parallel, as I have already told you while discussing TSC. I told you instead of having one TSC, we basically put many TSC branches in parallel and control them in a discrete manner. This is second TSC branch. We may have n number of TSC branches depending upon the reactive power compensation, how much leading wires have to be generated and injected into the transmission line. This is capacitor C3 and this is TSC S3. So these are my TSC branches. I will write TSCs, thyristor switched capacitors. These are parallel connected TSC branches. And then I will have thyristor controlled reactor, TCR, which is basically again a combination of TCR and TSRs, which is also called segmented TCR. So this is our TCR, which is basically a segmented TCR. And we may have a filter also. This is a filter, LC filter. This is harmonic filter. I will write here harmonic filter. So this is the schematic diagram of third type of SVC, that is TSC TCR SVC. You can see a number. This TSC TCR SVC comprises of a number of TSC branches which are connected in parallel, along with a TCR, which is a segmented TCR, and a filter, harmonic filter. Now, as far as these TSCs are concerned, they are not mechanically switched, they are not fixed, they are switched electronically with the help of this anti-parallel pair, pair of anti-parallel connected SCRs. Okay, we have already discussed individually about how a TSC works. Now, TSCs are switched in discrete steps. For example, we may switch in only TSC S1, switch S1, okay, depending upon the reactive power requirement. Let us suppose each TSC generates a reactive power of 10 megawatts. What is the total? C1, the TSC S1 generates 10 megawatts of leading wires or capacitive reactive power. S2 also same, and say S3 also generates, it's capable of generating same amount of reactive power. So therefore, what is the total MVA rating, or what is the total leading or capacitive reactive power generated when all the three TSC branches are switched on? So 10 plus 10 plus 10, that is 30 megawatts. So therefore, what is the MVA rating of the three TSC branches? The MVA rating of three TSC branches is 30. It's 30 MVA. Okay, which is of course all megawatts reactive power. Now, depending upon the reactive power requirement, let us suppose there is no reactive power requirement. The load is operating at unity power factor on the system, which is an ideal case. In that case, you don't need to generate, or you don't need to inject any leading wires, any capacitive reactive power onto the transmission system. So in that case, all the three TSC branches will be turned off. And what is the delay angle at which the TSC branch will be off? So in that case, alpha for all the three TSC branches will be 180 degrees. This is one way of putting the TSCs off. Another way is that your controller will not generate any control pulses. No firing pulses will be issued to the thyristors. So that is the other way of putting the thyristor switched capacitors off. TSCs S1, S2 and S3 off. Okay, but generally the firing pulse generator keeps on generating the firing pulses. The delay angle, the controller makes the delay angle equal to 180 degrees so that all the three TSC branches are off. Now let us suppose some reactive power requirement is there on the system. Let us suppose some industrial load has been put on, it has been switched on. So therefore our load is now operating at lagging power factor, and it demands the inductive reactive power. Now to compensate for that inductive reactive power, some of the TSC branches have to be turned on so that they inject the leading wires or leading capacitive reactive power onto the bus, and hence compensate for the reactive power requirement of the load. This is how shunt compensators work, we already know. Let us suppose load, the reactive power demand on the transmission line is say 15 megawatts. Let us suppose load draws an inductive reactive power of 15 megawatts. So therefore, how many, or let us say exactly it is, let us say it is 8 megawatts. The load requires, the load draws a reactive power of 8 megawatts. So therefore, our controller will turn on TSC branch S1, it will turn on this switch S1, and we know when switch S1 is turned on, it generates the capacitive reactive power of 10 megawatts. It injects that 10 megawatts into the system. But what is the reactive power requirement? It's only 8 megawatts. So the difference of the two, 10 minus 8, that is 2 megawatts, have to be absorbed by TCR. So our controller will simultaneously switch on TCR branch, and it will adjust the delay angle of TCR in such a way that it absorbs the difference of the two reactive powers. Difference of reactive power injected by TSC branch S1 onto the transmission line, and actual reactive power requirement of the load. So that 10 minus 8 is equal to 2 megawatts. So 2 megawatts of reactive power will be absorbed by TCR, by delay angle control, alpha control, right? Now let us suppose after some time, say after a couple of hours, more industrial loads are turned on, okay, and the load power factor deteriorates further and reactive power requirement of the load further increases. Let us suppose the reactive power requirement of the load increases from 8 megawatts to 15 megawatts by turning on of more lagging power factor load, industrial load. Okay. Now the reactive power requirement of load is 15 megawatts, and we have already TSC branch S1 on, which is injecting a reactive power of 10 megawatts, but now the reactive power requirement has increased from 8 megawatts to 15 megawatts. So S1 alone will not compensate this reactive power. So therefore your controller will switch on TSC branch S2 also. So when S2 is switched on, of course it operates both S1 and S2 at alpha equal to 90 degrees. They are fully on. So this also injects reactive power. S1 injects a reactive power of 10 megawatts. S2 also injects a reactive power of 10 megawatts. So what is the total capacitive reactive power injected into the transmission system by TSC branch S1 and S2? It is 10 plus 10, 20 megawatts. But what is how much reactive power you need to compensate? Only 15 megawatts. So the difference of the two, 20 minus 15, that is 5 megawatts of reactive power. There are 5 megawatts additional capacitive reactive power which are on the transmission line and which need to be absorbed. And therefore, the controller will adjust the delay angle of TCR. Of course, it will decrease the delay angle of TCR so that its susceptance increases and current drawn by it increases, and it absorbs more reactive power. Earlier in the previous case, it had to absorb only 2 megawatts. Now it has to absorb 5 megawatts of reactive power. So therefore, this balances the additional VARs or surplus reactive power, which is the difference of the two. Surplus capacitive reactive power is absorbed by TCR, by delay angle control. Now let us suppose after some time, more industrial load is now turned on and the reactive power requirement has further increased. Let us suppose the reactive power requirement, the total reactive power which is drawn by the load increases from 15 megawatts to 21 megawatts. This is the inductive reactive power which is drawn by the load. Okay, now S1 and S2, they too, when they are on, they inject a capacitive reactive power of 20 megawatts. But our reactive power demand has increased from 15 to 21 megawatts. So therefore, what will your controller do? It will immediately switch in S3 also. So S3 will also be switched in for at alpha equal to 90 degrees. Firing pulses will be issued to S3 and it will also switch in. So therefore, what is the total capacitive reactive power which is injected into the transmission line by the three by the three TSCs? 10 plus 10 plus 10, 30 megawatts. So total capacitive reactive power which is injected onto the line is 30 megawatts. But what is the reactive power which is needed to be compensated? Only 21 megawatts. So what is the difference? Difference is 30 minus 21. That is 9 megawatts of additional capacitive reactive power or additional capacitive wires or leading wires are there on the line which need to be compensated, which need to be absorbed. So therefore, the delay angle of TCR will be automatically controlled by or adjusted by the controller. It will be further decreased towards 90 degrees so that it draws more inductive current, and when it draws more inductive current, it absorbs more reactive power. Alpha will be adjusted at such a value that the TCR absorbs exactly 9 megawatts of surplus reactive power, capacitive reactive power, which is the difference of the two, and hence it balances for the surplus reactive power. Okay, so that load compensation, reactive power compensation is also done effectively, and there is no surplus capacitive reactive power flowing on the transmission line. Okay, so therefore the maximum reactive power which is to be absorbed by the TCR, it may be equal to the rating of one of the TSCs. The rating of each TSC I have assumed 10 megawatts. And how much reactive power for this case is absorbed by TCR? It is 9 megawatts, which is very close to 10 megawatts. Therefore, the rating of TCR is 1 by n, the rating of MVA rating of all TSC branches taken together. So I will write here rating of TCR is equal to 1 by n of total rating of SVC. In fact, total TSC rating is equal to this SVC rating. What is the total MVA rating? 10 plus 10 plus 10, for example, 30 megawatts. But what has to be the rating of TCR? Not 30 megawatts. It will be 1 by n of the total rating of SVC. And what is 1 by n in this case? How many TSCs are we using? For example, in this example, it is 1 by 3 of what is total SVC rating? The total SVC rating is the total MVA rating of these 3 TSCs. That is 10 plus 10 plus 10, 30 megawatts. So 30 by 3 means 10 megawatts. So therefore 10 MVAs. So therefore the rating of TCR, segmented TCR, will be 1 by n of total SVC rating. So therefore the size and the rating of this TCR is least. It is the minimum of all the 3 SVCs taken together. We have already discussed the other type of SVCs. In fact, in FC TCR type SVC, the rating of TCR is largest, and the rating of TCR is minimum for this type of SVC. I have explained that with the help of this example. So therefore, TSCs in this TSC, TCR, SVC, the TSCs are switched in discrete steps, and continuous reactive power control in each step is performed by TCR. For example, if only S1 TSC is turned on, then alpha control is done for TCR and it performs the continuous reactive power control. The additional or surplus leading wires are absorbed by alpha control. If S1 and S2 are turned on, say earlier only S1 was switched in, now in a discrete step, in second step, S2 is also switched in. Then again, alpha control of TCR is done and it performs the continuous reactive power control. If third TSC branch is turned on in next step, then again this performs the alpha control. Alpha control is done, or continuous reactive power control is performed by the TCR. In any case, whether only one TSC branch is turned on or a number of TSC branches are turned on, the TCR needs to perform the reactive power control, and its rating has not to be equal to, if all the 3 TSC branches are turned on, its rating, the rating of TCR need not to be equal to the total rating of all the 3 TSC branches. Its rating will be the rating of only one of them. Okay, 1 by n. Okay, 1 by n times total TSC branch ratings, or 1 by n times total SVC rating. That I have already explained. Okay. Now, since TCR in this type of SVC is smallest, there will be reduced harmonic content in transmission line currents. Smallest the TCR, smaller will the magnitude of reactive current it is drawing. Smaller the magnitude of reactive current, smaller will be the harmonic content in the transmission line currents, and lesser will be the filtering requirements. Okay. Now, just like FC TCR type SVC, which we have discussed in the last class, where each capacitor bank is connected, in each capacitor bank we connect a tuned reactor in series with each capacitor bank. For example, if you remember, we had a Y connected or star connected capacitor bank, and in series with each capacitor we are connecting tuned reactor, so that each and this reactor and capacitor in series, it forms at fundamental frequency, it injects the reactive power, it acts as a capacitive admittance and injects the reactive power onto the bus, and at a particular harmonic frequency the inductor design is done in such a way that the tuned inductor, for example, if I put a small inductor in series with this TSC branch, the inductor is designed in such a way, for example, I want to suppress 11th order harmonic of line current. If 11th order harmonic is the most predominant harmonic of current flowing in the line, transmission line current, then I want to suppress it. Then the inductor which I put in series with the TSC branch, in series with this capacitor, it is to be designed in such a way that this L, it becomes a tuned, single tuned filter, tuned to 11th harmonic frequency, and 11th harmonic frequency has a frequency of 11 times the fundamental, that's 11 into 50 hertz, that is 550 hertz. So therefore this filter is designed for 550 hertz, 11 times fundamental, and it eliminates the 11th harmonic. Similarly, the second TSC branch has also a small inductor, tuned inductor in series with the capacitor, and that tuned inductor is designed in such a way that it suppresses the 13th order harmonic in that transmission line current. So it acts as a single tuned filter for 13th harmonic component of current. And what is the next higher order harmonic component of current flowing in the transmission line because of TCR? It is 17th. If we have third TSC branch, in this TSC branch also in series with the capacitor, we place a tuned inductor or reactor in such a way that it acts at the 17th harmonic frequency. This branch acts as a harmonic filter and it suppresses or eliminates 7th harmonic component of this 7th harmonic component in the transmission line current. Okay. So therefore each TSC branch at fundamental frequency acts as a capacitive admittance, individual capacitive admittance, and this TSC branch at fundamental frequency injects a desired amount of reactive power into the transmission line. But at particular harmonic frequencies, each TSC branch acts as a tuned filter for the suppression of those particular harmonic frequencies of transmission line current, which are there because of the TCR current flowing. Now, in case of FC TCR SVC, the capacitors were permanently fixed. There was no switching. Okay, but in this type of TSC, if there is no reactive power requirement of the load, if load is, for example, operating at say unity power factor, or during the light load hours, generally all industrial load is off, and during late night hours, light load hours, you don't need to inject any capacitive reactive power. So what will your controller do? It will switch off all the TSC branches. So when all the TSC branches are switched off, then TCR branch is still working, because during light load hours there are leading wires flowing on the transmission line and those need to be absorbed by TCR. Since TCR is continuously conducting, it's continuously on, it absorbs the excessive or surplus reactive power, whereas all the TSC branches are turned off. A situation arises where there is no harmonic filter, because when this TSC branch was switched in, it was on, it was acting as a harmonic filter for 11th harmonic and suppressing that 11th harmonic. This was suppressing 13th harmonic, this was suppressing 17th harmonic, and if you have more number of TSC branches, so more number of harmonics are suppressed. But in a situation where all the TSC branches are switched off, a situation arises where there is no harmonic filter. TCR is drawing the currents, and there will be large distortion in the transmission line currents, which is problematic. To avoid such a situation in which all the TSC branches are turned off and there is no filter, harmonic filter connected to the line, an additional filter, harmonic filter, is always connected in parallel with these branches, so that when all these TSC branches are turned off, there is still some sort of filter which filters out some harmonic content in the line current. Okay, so that is why this additional filter is always kept there, to avoid a situation where all TSC branches are turned off and TCR is conducting and it is resulting in harmonic current. A non-switchable harmonic filter is always connected in the system. Okay, so that is it. Now let us try to discuss about operation of this type of SVC, operation of TSC, TCR, SVC. As I have already told you that the operation of this type of SVC, that is operation of TSC, TCR, SVC, is divided into n intervals. I will write here in first interval. Only one TSC branch is turned on. Let us suppose TSC switch S1 is switched in. S1 TSC is switched in. Switched in means turned on. So therefore it performs the reactive power control, and the reactive power is controlled from 0 to QC max by N, where what is QC max? QC max is the maximum capacitive reactive power which is generated when all the TSC branches are turned on. But in the first interval, we are turning on only one TSC branch, S1. So therefore, with the help of TCR branch, the reactive power control from 0 to QC max by N is performed. Because for example, if there are 3 TSC branches, each operating 10 plus 10 plus 10, 30 MVA, so how much is the reactive power control in the first interval when only one TSC branch is turned on? 0 to 10 megawatts. That means 0 to QC max by 10. QC max is 30, 30 by 3 is 10. So 0 to 10 megawatt reactive power control is done. Let us suppose reactive power demand of the load has increased. So in the second interval, your controller will switch in second TSC branch. Okay. Then I will write in second interval S1 and S2 are switched on. S1 was already on, S2 is also switched on. So therefore, how much reactive power control is done? Reactive power control is QC max by N to 2 times QC max by N, because now 2 TSC branches are on. In third interval, third TSC branch is turned on and reactive power is controlled from 2 QC max by N to 3 times QC max by N, and so on till you reach nth interval. Nth interval will be decided by how many TSC branches we are connecting in parallel. That depends upon how much reactive power compensation is to be done. So in nth interval, finally, the reactive power control is done from N minus 1 QC max by N to N times QC max by N. N and N goes. That means from N minus 1 QC max by N to QC max, because N and N goes QC max. That means when all the TSC branches are on, what is the total reactive power control? It is from N minus 1 QC max by N to full QC max. That means when all the these TSC branches are on, and suppose TCR is not turned on, then maximum reactive power which is injected into the bus is QC max. And if TCR is turned on, it performs the reactive power control by absorbing some of the reactive power. Then the reactive power control is from N minus 1 times QC max by N to QC max. Okay, this is how it is operated. And with the help of characteristics, I can show the operation like this. Let me show it with the help of characteristics. This is QL demand, inductive reactive power demand along this positive x-axis, along negative x-axis it is QC demand, capacitive reactive power demand. Okay, so this is inductive operation. This shows your SVC operating in the inductive region, and this shows operation of this operation in capacitive region, operation of SVC in capacitive region. Let us suppose we want to control our reactive power in this way. This is the reactive power Q. This is Q, which is equal to QL alpha minus QC. Okay, what is the total reactive power which is injected onto the line? What is the total reactive power compensation? The reactive power which is injected by TSC branch, which are basically capacitive branches, QC, and some of the reactive power is absorbed by the TCR by delay angle control, and how much reactive power it absorbs? QL alpha. So the difference between the two is the total reactive power compensation which is done by this SVC. And how is it done? Here it shows it is done linearly, but it is not, it is done something like this. You can see, I can show it here, capacitive operation, capacitive range. It is done like this. First, C1 or S1 is switched in. Okay, S1 means this switch is switched in. Then S2 is switched in, and then maybe after some time S3 is switched in. This means switching in of TSC branch depending upon the requirement. And then TCR works like this. Let me show you the operation of TCR. Please bear with me. Let me first of all draw, then it will be clear. TCR works like this. This is how TCR works. This is QC, okay, and this is QL, which is a function of alpha. Here alpha is equal to, at this instant, alpha is equal to 180 degrees. Let us suppose the maximum reactive power compensation has to be done so that all the TSC branches, which are 3 in this case, have to be turned on. So S1 is on, S2 is on, S3 is also on. So when all the 3 TSC branches are on, how much capacitive reactive power is generated by our TSC branch? This much. And therefore it does the reactive power compensation. Let us suppose TCR branch is off, okay, and let us suppose all the reactive power which is generated by these TSC branches, it is used for load this inductive reactive power compensation. So therefore this much is the reactive power which is injected and reactive power compensation is done. Let us suppose that after some time some of the industrial load has turned off and load power factor has slightly improved, so the reactive power requirement has decreased. Suppose reactive power requirement of the transmission line or reactive power compensation of the transmission line requirement that has decreased from this to this. But when all the 3 TSC branches are on, how much reactive power is injected? This much. But how much reactive power is actually to be injected into the line? Only this much. Okay, so therefore now your controller will adjust the delay angle of TCR in such a way that the excess or surplus reactive power, which is surplus reactive power means which is the difference between what is the reactive power requirement and what is the reactive power actually injected by all the TSC branches. That surplus capacitive reactive power is to be absorbed by the TCR branch. Okay, so therefore what will your controller do? It will turn on earlier TCR was off, alpha was 180 degrees. Then at this point it will adjust the delay angle of TCR so that this much is the reactive power which is absorbed by the TCR, and this reactive power which is absorbed by the TCR is equal to the difference between the two, so that the net reactive power which is injected onto the line is this much. And therefore by continuous delay angle control we can do we can control the reactive power in a linear manner. You can say continuously like this, here, 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 here. Let us suppose now after some time the reactive power compensation requirement has further decreased and you don't need all the 3 TSC branches to be turned on. Then what will you do? S1 was on, S2 was in, S3 was in. After some time S3 has to be turned out. I will write S3 out. Now S3 has to be turned out. So S3 will be off by making its delay angle equal to 180 degrees. So it will be off. Only 2 these TSC branches are now on. You can see S1 is on and S2 is on. And how much reactive power it's injecting? This much. And from this to this, reactive power control will be again done by this TCR control. Again here, delay angle is 180 degrees and then delay angle is decreased if reactive power, more and more reactive power is to be absorbed, and then this is the reactive power absorbed by the TCR, and when alpha control is done, this is the capacitive reactive power injected by S1 and S2 together, and this is the inductive reactive power or reactive power absorbed by TCR, and this minus this gives the total reactive power control. You can see over this range. Let us suppose after some time the load power factor has further improved and you need only 1 TSC branch in the system. So therefore what will you do? S2 will also be out. I will write it S2 out. Only S1 will be on. And when S1 is on, and if this much is the reactive power demand of the load, then TCR is again turned off. It is operated at alpha equal to 180 degrees. But if the reactive power demand of the load further decreases, say it is here, it decreases, then TCR is again controlled, its delay angle control is done. alpha is decreased from 180 degrees towards 90 degrees so that it absorbs the surplus reactive power and it performs the reactive power control Q, which is equal to QL alpha minus QC. And if no reactive power is to be injected into the bus, then you may have to operate your TCR at a lower value of delay angle very close to 90 degrees, so that whatever reactive power is generated by this capacitive branch, TSC branch, all that reactive power is absorbed by TCR, and net reactive power injected onto the bus is 0. And now if you want to operate your SVC in the inductive region, okay, then this is how you operate it in the inductive region. Maybe somewhere here alpha is 90 degrees. You need to, when you need to operate it in the inductive region, all the TSC branches have to be turned off. And there may be, during light load hours, there may be a capacitive reactive power, leading wires flowing on the line, and at that time only TCR branch has to be turned on, and its alpha control is to be done, and it operates in the inductive region and absorbs the surplus or excess reactive power. Okay, so here S1 is also off. So therefore, this is when all S1 is on, S2 is on, S3 is on, reactive power control by TCR. Then if only S1 and S2 is on, from this to this in the second interval, reactive power control, you can say Q control, is done by TCR, alpha control, as you can see. If only S1 TSC branch is on, then from this interval to this interval, that means in the third interval, reactive power control is done again by TCR alpha control, you can see. Okay. Now you can very clearly see that when S3 was earlier on, when S3 has to be turned off, S3 out, it is out here, and at same instant this TCR also has to be turned off, alpha has to be made equal to 180 degrees. But this cannot be done simultaneously, there is always some delay. There is a delay in turning off of this TSC branch and turning off of this also. Okay, so therefore what is done, instead of turning off this TCR branch here, it is delayed by a few microseconds, maybe a few milliseconds or microseconds. So it is turned off somewhere here. Okay. Then similarly turned off somewhere here. It's turned off somewhere here. Okay. So therefore, this gives a hysteresis between turning on, turning off, and switching off, and switching out and switching in of TSC branch. That's called hysteresis, I mean delay between the two. So, and one more thing is that because it is delayed, the switching off of TCR branch is delayed by a few cycles, the rating of TCR branch will be slightly higher than what you have calculated. Okay, so this is how the operation, this is how this operates, this is how TSC, TCR, SVC operates, and how continuous reactive power control is done with the help of this TSC branch and by delay angle control of TCR. Okay, I hope this is clear. Now, total reactive power, which is controlled, it is given by applied voltage times IL alpha minus sigma ICN. V into IL alpha is inductive reactive power, which is absorbed by TCR, and IC1 plus IC2 plus IC3 is the total capacitive reactive power. V into IC1 plus V into IC2 plus V into IC3, so on, is the total capacitive reactive power, which is injected by TSC branch. So the difference between the two reactive powers, this is basically Q equal to QL alpha minus QC. This gives the total actual reactive power which is injected into the line, and which shows how a reactive power control is done. Okay, so I hope this is clear. Now, after this I will discuss with you functional control scheme. Or should I continue or leave? Okay, let me leave my lecture here. I will continue. The second part of the lecture will be in next lecture. Next lecture will contain the second part, concluding part of this type of SVC. I have decided to divide it into two parts. because if I discuss all this type of SVC in one lecture, the duration of lecture may go beyond 1 hour, and it may be difficult for you. It may create difficulty for you to watch continuously for more than 1 hour, or say 1.5 hours. So I have decided to break the discussion on TSC, TCR, SVC into 2 lectures. Today was the first part of this lecture, and in this lecture we have first of all studied the schematic diagram of TSC, TCR, SVC, and we have seen that a number of TSC branches are connected in parallel along with TCR and a filter. TSC branches are switched in discrete steps, and continuous reactive power control in each step is done by the delay angle control of TCR. We have also studied that, we have also learned that rating of TCR is 1 by n times total SVC rating. We have also seen, since the rating of SCR is very, very small, there is reduced harmonic content in the transmission line currents. And each TSC branch has a tuned reactor to suppress the predominant harmonics at particular harmonic frequencies. I have also told you that to avoid a situation where all TSC branches are turned off and harmonic current is still flowing due to the operation of TCR, a non-switchable harmonic filter is always connected in this type of SVC. Then with the help of this characteristic or diagram, graphical pictorial representation, with the help of this graph which I have discussed with you a few moments back, we have tried to understand the operation of TSC, TCR, SVC. Okay, its operation is very simple. The total reactive power compensation is V times, I will write again, Q is equal to V times V is the voltage across voltage across SVC, V times IL alpha minus sigma ICN. That is Q is equal to QL alpha minus QC. Okay, and how this reactive power control, continuous reactive power control is done? It is done in a step manner. First, you may have turned on all the TSC branches. Then reactive power control is done by alpha control of TCR, and then you may have to switch out some of the TSC branches, and then in different steps, by alpha control of TCR branch, continuous reactive power control is done. That we have tried to understand with the help of graphical representation, with the help of graph, with the help of characteristics. So more on it in next lecture. I advise all of you to go through this lecture, and in case of any doubts, please feel free to ask. Thank you.